Hello, welcome to my presentation. My name is Joao Rivera, and I will present the work that I did with my supervisor Markus Püschel from ETH Zurich and with Franz Franchetti from CMU University. The title is A Compiler for Sound Floating Point Using Affine Arithmetic. Well, let's start with an example. Imagine that you have this code. And I mean, it's very normal. It does some floating point computations in double precision. And you feed some inputs and you want to know how accurate the result is. Well, if you only look at the result, it is not possible that you can know this because floating point is not sound. I mean, every floating point is finite precision, so every operation you will get some round of errors, so you don't know how large this will become. So I wanted to point what soundness is in this context because it's in the title, sound floating point. So we mean by this that the result that we get has warranties, has accuracy certificates in the number of correct bits in the result. So error bounds, basically. So you may ask then how to make the code sound. And well, one of the options is to transform it into or write it using libraries, using interval arithmetic, for instance, which is known with sound. And obviously, I mean, interval arithmetic, it has lower bound and upper bound, so you will be performing more operations, but it's going to be sound. So in this case, it's 6 times slower. I mean, it's fine, it's not that bad, and you get soundness. However, for this specific example, you don't get any bits. So the final accuracy is 0. So the interval just grew a lot and you lose, you lost all the precision here. So this is a particularly nasty example for interval arithmetic, for instance. So why does this happen? Well, this is because of the way intervals work. For instance, here we have an interval A, that goes from 0 to 1, and we want to compute A minus A. Well, in this case, it would be this. However, when you perform this computation in interval arithmetic, the result is the interval minus 1 to 1. So this is not what we expect. We expect 0. But the reason is that interval arithmetic does not keep correlation between variables. So it actually performs this operation as if both were different intervals and not the same. There is another technique called affine arithmetic, which is also in the title of this presentation, which basically represent variable or values by its center value and by error symbols. So for instance, for A, which has a range 0 and 1, the center value is 0.5. And then we have an error symbol, epsilon 1 with coefficient 0.5. And epsilon 1, this is an error symbol, a symbolic variable. And all of them always have the value of this interval from minus 1 to 1. And when you perform this operation, the same operation, but now in affine arithmetic, and now you see that this symbolic variable is propagated to the computation, and this keeps correlation between variables. And actually, the final result is the actual result that we expect, which is 0. So this is like the beauty of affine arithmetic, that it keeps a linear correlation between variables. So okay, this is good. Then the same computation, you find a nice affine arithmetic library, and you do it in affine arithmetic. And now you get 40 bits of precision. This is great. In interval arithmetic, it was 0. However, you run performance, you test, and you realize that it's 10,000 times slower than compared to the original program. This is a lot. So then you see a trade-off between the interval arithmetic, which is less precise but faster, and this full affine arithmetic that is very precise but way slower. So why is it slower? It is actually because of the error symbols. I mean, in affine arithmetic, every operation, it introduces a new error symbol in order to make it sound. Every operation. So you can imagine this in a loop. You perform a lot of operation, and then just the error symbols grow. And then when you perform an addition and a multiplication, which depend, the cost of this depend on the number of symbols, then it just, I mean, explodes at some point. It's a lot, which is exactly what will happen which is happening in this example. So what we propose is a SafeGen, and we propose to use affine arithmetic, but instead of growing the number of symbols in variables indefinitely, we limit the number of symbols. We impose 1k. So only this variable can have at most k symbols. And we implemented vectorization techniques in order to do the implementation as fast as possible. And this is actually a source-to-source compiler. So what it does is take the C function and it transforms it into an equivalent function that uses affine arithmetic with the library that we provide, of course, with this limited number of symbols. And in this case, for k equal 8, for limiting the number of symbols to 8, we have 24 certified bits and is 60 times slower compared to the original program. So you see the trade-off. It's a trade-off between accuracy and performance, and we are in between the less accurate interval and the very expensive and accurate affine arithmetic, full affine arithmetic. So this is how SafeGen looks like. So as input, you have this C function performing some floating point operations. You can specify some target precision for the affine data type, which can be single, double, or double-double. And you specify the limit on the number of symbols for each variable. And I mean, SafeGen has two main parts, which is the preprocessing part that performs some analysis, some static analysis in order to improve accuracy. So I will discuss this later. But basically what it does is identify symbols which are likely to benefit accuracy and try to preserve those in order to preserve accuracy. And the other one is called transformation that I will talk right now, basically. And as output, we get this the same function as in the input, but performing the same operation, but soundly using affine arithmetic. And it has to be sound, it has to be hopefully fast, and hopefully as accurate as possible, of course. So maybe let's start with the transformation that it does. I mean, for instance, everything is very straightforward. I mean, we have declaration nodes, we construct the AST, and every floating point declaration is transformed into a affine type declaration. Same for expressions. For instance, this multiplication is transformed into an affine multiplication, so to a function called to our affine arithmetic library. And also constants, for instance, 0.1 cannot be exactly representable in floating point. So then we define this new affine arithmetic variable, which has 0.1 as a center value, plus some small error symbol that in order to enclose the value of 0.1 in order to make it sound, basically. So this was the transformation. So I want to emphasize a bit more about how we limit the number of symbols. So imagine that after some computations, you get this X with n symbols. So, and we want to limit the number of symbols to 3, at most 3 symbols per variable. Remember, x0 is just a center value, and epsilon1 to epsilon n are the symbolic variables, the error symbols, basically. So what we do is basically take many of those error symbols and fuse them together into one new error symbol, in this case, epsilon n plus 1. And all the coefficients are just added together and the absolute value of them, basically. And at the end, we get this new X with only 3 error symbols. And as you can see, I mean, we lost a lot of error symbols. So this is a trade-off between accuracy and performance, basically. We have less symbols now, and therefore less correlation, but it's going to be faster, of course. So the real challenge, actually, and I want to emphasize this, is to choose what symbols to fuse and to really do this in a good way to not affect accuracy, or to try to not affect accuracy that much and still have good performance. So in order to do this, we support many fusion policy, where a fusion policy is just a rule that defines what symbols to fuse, basically. And here I will explain two that perform quite well, or just to give an idea. So for instance, assume that we define k equal 3, and we have these two variables with these three arrow symbols each. And if we perform an addition, we have the result that has 4 arrow symbols now. So the first policy is the oldest symbols, and we decide to fuse the oldest symbols. So we define oldest in terms of the identifiers. So in this case, it's going to merge epsilon 1 and epsilon 3. So 4 plus 1 is 5, and it's going to place the new arrow symbol in epsilon 6, basically introduces a new arrow symbol. And the other policy that we support, or another one, because we support more, is the smallest absolute values are merged, are fused. So for instance, 1 and 2 in the coefficients are the smallest values. So these symbols are chosen to be fused in a new one. And here you can see that these two fusion policies have different results, right? Keep different symbols at the end. So they have different trade-offs at the end, and they will have different accuracy at the end. I mean, fusion policies are nice. We support them, but they only can keep information regarding like the identifiers and the coefficients. So they don't really see like the actual computations or how a symbol will correlate maybe in a future operation. So this is why we perform DAG analysis as well, in order to prioritize some symbols. So I will explain this now. For instance, assume that we have this computation, very simple, 2 multiplication, and then we subtract. And so we construct the DAG for this, and the first 3 nodes are just the variables. So let's assume that they are here, and every node is annotated by the error symbol that it creates. So the first are just the error symbols of the initial variables. Then the multiplications, I mean, as you can see, we define k equal 5. So if you see the result here, we end up with 3 error symbols for each. So it's still fine. We don't have to fuse anything. And the final subtraction, as you can see, it has 4 error symbols. However, what is interesting here is that epsilon set in this example just cancels out. And this is because of the final subtraction, right? We have 2 symbols in T1 and T2, and both have epsilon set, and they cancel out in the subtraction. So this is actually interesting. So this is the property that I want to emphasize, that we call this reuse. So reuse is when an error symbol can arrive to a node from 2 different paths. We say that this error symbol has reuse, and it's likely that it will cancel out. It could be that it will not, but it's likely as well. It depends on the values that it has as well, the coefficient, but it can cancel out. And as you can see, epsilon set is the only one that has this property. So we really want to keep this one because it's the only one that has reuse and the only one that can cancel out. So for instance, here, let's assume that now we reduce k to 2. So now we have a problem in the multiplication in T1 and T2 because we have 3 symbols, but now we have k equal 2. So we have to merge, we have to fuse 2. And obviously, because epsilon set is the one that has a reuse property, we want to prioritize this. We don't want to fuse this. And then we have to fuse the other ones in order to still have some benefit of cancellation at the end, of canceling out this symbol. So basically, I introduced this reuse property. And I said that we want to prioritize the symbols in a node. So what I mean with prioritization is that when a symbol is prioritized in a node, it is protected from fusion. So it will not be fused. in this node. And for this DAG, I mean, it's immediately clear that epsilon set has to be prioritized in nodes T1 and T2 in order to have in order for it to cancel out at the last node and have some accuracy improvement. So actually the problem that we want to solve here is that to find symbols to prioritize in each node to maximize reuse under certain constraint, and the constraint is that every node at most can prioritize k symbols, which makes sense because k is the fixed number of symbols of each node. So this is at most the number of symbols that can be protected from fusion, basically. Of course, this is an optimization problem. By the way, in reality, it's not k symbols, it's k minus 1, but I will not get into details, but this is just a minor detail. And as you can see, this can be modeled. I mean, this is looks a lot like an optimization problem, and it is actually one. We want to maximize something, reuse, in order to find the prioritization of each symbol in the nodes, subject to certain constraints. So we can model this as an ILP program. And what we do, this is exactly what we do. We have a computation, we construct the DAG, we analyze it, the DAG to identify the reuse property. We feed it into, we construct the ILP program and we feed it into an optimizer, in this case, Gurobi. And as a result, we get for each node, the error symbols that have to be prioritized in this node to maximize reuse and hopefully improve accuracy. And it will likely improve accuracy, as you will see in the results. Actually, right now, you will see in the results. So, I mean, here are a lot of things happening, but I mean, what is important to understand is that all of these are different configurations of exception. So we play a lot with all the fusion policies. We have also placement policies, and we have prioritization when we have this DAG analysis and so on. And maybe what is most important is that are these red dots, which means that we use the smallest policy, as I discussed. We use prioritization, which is this DAG analysis, and we use vectorization techniques. And as you can see, I mean, the y-axis is a slowdown compared to the original program, and the x-axis is certified accuracy. So the more accuracy, the better, and the lower slowdown, the better. And as you can see, the red dots are in the Pareto front, mainly, which are the ones that are prioritized. Something that is interesting is, for instance, this blue one is almost exactly as the red one, which both use the same policy, smallest policy. Both are vectorized, and one is with priority and the other one without priority, blue one without priority. And I mean, we have different dots because we have different values for k. For instance, for k equal 8, the red dot, and k equal 8, the blue dot, the only difference is that one we use DAG analysis and the other one we don't. And you can see it immediately that this is more or less 10 bits improvement just using the DAG analysis. Of course, it has some overhead, and this is why it's almost overlapping with next node, which I think is k equal 12 for the blue one. So actually in this benchmark, it's more or less the same, the blue one and the red. But in the other benchmarks, always the red one is the one with prioritization is normally in the Pareto front as well. Something that I want to point out is that these little guys here, this is using random fusion. So this is why it's good to emphasize that fusion policies are important. I mean, this one is just choosing symbols randomly, and you can see that just the accuracy, all the accuracy is lost. So it's really important to choose one that is smart, not only random. And this is another benchmark, and you can see, I mean, this looks a bit better. As you can see, the one with prioritization and vectorization and the smallest policy, this red one is the Pareto plot. Pareto front, sorry. Some nice observation is that, I mean, prioritization improves accuracy by between 4 and 8 bits, and it has 25% of overhead, more or less, because you have to compare that the symbols that you don't want to fuse if they happen in operations, so you have some overhead. And vectorization improves between 1.2 and 3 times the speed, so it's faster with vectorization, which is expected, of course. We now compare our approach with X16 libraries, for instance, for affine arithmetic libraries and interval arithmetic libraries. And the red dots are the same as the previous plots. Actually, these are the same benchmarks, but now we choose our best, which is the Pareto front, and we compare with libraries, basically. So the white dots are interval arithmetic with double and double double, and you can see just all the accuracy is lower. And the triangle is the full affine arithmetic, which is the most accurate, is expected, but it's way slower as well. It's like 4 order of magnitude slower. It's a lot. And the gray points are another affine arithmetic library, which also has this limited K, but they use a different kind of policies, and it's implemented in Scala. So since it's implemented in Scala, I mean, it's expected to be slower, at least for 10x, I would say. But it's interesting that we achieve, for instance, more accuracy here due to the prioritization, the tag analysis that we are doing. Just some facts. I mean, we are between 30 and 70 times faster than Ceres affine. These are the gray dots, gray points. And we are between 10 and 36 slower than interval arithmetic, but of course we are way more accurate as well. Maybe to finalize, just a summary. I mean, we introduced SafeGen, a compiler for sound floating point using affine arithmetic. And this performs a tag analysis in order to improve accuracy. And it transforms each operations into an affine arithmetic operation. I explained these fusion policies that are important to decide which symbols to fuse. And the tag analysis to decide which symbols to prioritize, which symbols not to fuse. It's kind of the contrary. I presented some extended evaluation between different configurations of SafeGen and against other libraries. And we see that we are between 30 and 70 times faster than other libraries in affine arithmetic, while we are more accurate than compared to interval arithmetic. So I think that concludes my presentation, and thanks for listening.